Hello, game theorists. So today is our practice session. As described earlier, there are two sections to our exam. There's the short answer section, and there's also the problem section. So the short answer section is more verbal and intuitive. The problem section is mathematical. So let's get started on our short answer section. Question number 1, define Nash equilibrium. So we gave this definition in class. So Nash equilibrium is the strategies, not the payoffs, and I emphasize that quite a bit. So the strategies are Nash equilibrium if no individual player can change strategies and get a higher payoff. So that was pretty easy. An equivalent definition that we talked about was if each player is playing mutual best responses. So my strategy is the best response to your strategy, and also your strategy is a best response to my strategy. That would have also been full credit. All right, moving on. Number 2, that talks about the prisoner's dilemma. Now, in this variant, prisoner 2 has a strong sense of loyalty, and they decide to not confess. Does that make prisoner 2 irrational? And the answer is no. That's because the payoff can depend upon things like loyalty and not just time in prison. We gave several examples where other considerations other than money or other than years in prison, in this case, could impact a player's payoff function. This is especially relevant in some of the in-class games. So if prisoner 2 places a higher value on loyalty than on years in prison, then it's rational to not confess. So we said several times that when the results of a game appear to contradict theory, what's really going on usually is that the payoffs have been misspecified. Saying people care only about money or care only about years in prison is an oversimplification. The results sometimes end up proving that there is more to the story, that there's other things like loyalty or cooperation that are part of people's values. And if you were to somehow incorporate those, kind of hard to do that, but if you somehow could, then the results would be consistent with game theory. let's move on to the problem section. This should be a -W. My printer just could not print in that edge of the page. So problem number 1 was about a continuous strategy simultaneous move game. So Wesley's first time goes to W, so he's picking W and B for Ben. And we have these payoff functions. Our mission is to find the pure strategy Nash equilibrium or equilibrium. Could be more than one. So let's do that. So I'll start with Wesley. Wesley's payoff, so pi W is Wesley's payoff, minus 5W squared plus 7 minus B times W minus 21. How do we maximize this function? We take partial derivatives and set them equal to 0. So Wesley picks W, so we take the partial derivative with respect to W. First we apply our power rule to this term. That becomes minus 10W. Now we go and work with the second term here. Because we're taking the derivative with respect to W, the terms that are not W, that is the 7 minus B, get treated as if they are constants. So you saw an example like this in your calculus class, like y equals 8x. You find dy dx, you get 8. So the constant is what remains when you have a situation like that. In this case, we're treating the 7 minus b as if it were a constant because b is not w. We're taking with respect to w here, not with respect to b. So constant survives just like I did back here, and a w goes away just like that x went away. Now this last term here, minus 21, that's a constant. Derivative of a constant is always 0. So we set that partial derivative equal to 0. Now we do the same thing for Ben's payoff. So Ben's payoff is minus b squared w minus 4b minus w. Partial derivative with respect to b because Ben picks b. Power rule in this first term gives us minus 2b. Now, for the second term, we get w minus 4. It's just like this one over here. So the stuff that's not a b, the w minus 4, that's treated like a constant, and the derivative of that's going to be just a constant, and the variable is going to go away. Just like it did back here, and just like it did over there. That partial derivative equals 0. So we get these two equations. We're going to use them to solve for the two unknowns, w and b. Let's see, how do I want to handle this? Let's go rearrange this one first. So I get w equals 4 plus 2b. So I just pushed these guys to the other side. Why I did that is so I can substitute this in for w up over here. What does that yield? Let's continue down here. So I have minus 10 times w, but I just established that w is 4 plus 2b, so I plug that in. Plus 7 minus b equals 0. Let's expand. So I get minus 40 minus 20b plus 7 minus b equals 0. Combine like terms. Minus 33 minus 21b equals 0. Push that 21b to the other side. Divide everybody by 21. And we get that b equals, that should simplify to minus 11 over 7. They're both divisible by 3. That's how I know that. So you can factor out a 3 and cancel. Now we have b in hand. We can plug it in over here to find w. So w is 4 plus 2b, but b is minus 11 over 7. So that gives us 4 minus 22 over 7. 4 to get a common denominator is going to be 28 over 7. And that comes out to 6 over 7. So that's how you do number 1. You can see I have a mix of harder and easier problems. This over here is substantially more complicated than defining what a Nash equilibrium is. So there's going to be a mixture of difficulty on the exam problems. They won't all be easy. They won't all be hard. All right, moving on. Problem number 2, we have this sequential game. This one's actually called the Centipede Game because these branches here look like legs. So it looks like this bug has a ton of legs, so hence the name Centipede Game. Our mission, find the rollback equilibrium equilibria, in case there's more than one. So the payoffs are always player 1's first, then player 2. With rollback, you go to the end of the game, which would be right over here, and we find out what happens there and work our way towards the front. So player 1 here could play take and get 16. Alternatively, player 1 could play split and get 8. Getting 16 is more, so they'll play take 5. So we draw an arrow. Let's back up a step. So player 2 is over here. They know that player 1's going to take on the next turn. And when player 1 takes, that means player 2 is stuck with a whole bunch of nothing. So player 2 would rather play take 4 and get 8 than play double and eventually get 0. Let's go back one more step. Player 1 is over here. Player 1 knows that player 2 is going to play take next turn. If that happens, player 1 gets nothing. Therefore, it's better for player 1 to play take 3 and get 4 instead of doubling and getting 0 down there. By the same reasoning, player 2 over here would rather play take 2 and get 2 instead of getting 0. That means at the very beginning of the game, player 1's going to play take 1 and get 1 rather than continuing and getting 0. So in this game, you see how the players would cooperate. They always play double, then split at the end. They would both get 8. Instead, though, what's going to happen in the rollback equilibrium is player 1's going to play take 1 and game just ends. Now remember, with the rollback equilibrium, you gotta specify each player's complete strategy. Even though player 1 plays take 1, the game just ends right away, you still gotta specify what they would do in case they found themselves at this node or at that node. Same for player 2. The reason we said that is because there's always some mistake that player 1 plays double by mistake. So the rollback equilibrium is player 1 plays take 1 at that node. If they get this node, they play take 3. At that one, take 5. Player 2 plays take 2 if they get to that node. They play take 4 at this other node. So that is your rollback equilibrium that specifies each player's complete strategy. Very last problem. We have this game over here, and we're trying to find the pure strategy Nash equilibrium or equilibria. Could be more than one. So if Andre plays N, what is Kyle's best response? Kyle is our row player. Row players' payoffs always come first, so Kyle's, look at these numbers here. So he could play X and get 2, or he could play Z and get 2. It's kind of hard to see my underline, so I'm just going to circle it instead. If Andre plays S, Kyle's best response is to play X and get 1. If Andre plays E, Kyle's best response is to play X and get 4. That's better than getting 3. If Andre plays W, best response is to play Y and get 3. Now let's do the same exercise for Andre. Let's say Kyle is playing X. What does Andre want to do? Andre, as our column player, has the payoffs that come second. He cares about the second number here. That's biggest when he plays N, because that gives him 3. These other options give him lower payoffs. Now I found one Nash equilibrium already, but don't stop there. There could be multiple equilibria, so just finish up the best response analysis so you don't miss any equilibria. What if Kyle plays Y? Andre's best response is to play W and get 4. Everything else is just worse. You see, I found another Nash equilibrium, so it's a good thing I didn't stop when I found that one. Last possibility, Kyle could play Z. In that case, Andre's best response is playing E and getting 7. So our pure strategy Nash equilibria are XN and YW. So that wraps up our practice session. Be sure to study hard and stay safe out there, and best of luck on the exam.